Okay, so now we're actually going to, like we said last time, everything that we've done up until now has just been describing the problem. We haven't really solved it. Today we're going to start to try to solve the critical section problem. Now remember, at the end of class last time, or towards the last half of the class last time, we said this is the general format of the critical section problem. We have two processes that are looping concurrently, and each one has a critical section where it's important that interleaving not happen in order for the solution to be correct in the end. And so we label that the critical section, and basically it's kind of like this. What you do is, you put a gate in front of the critical section, which is a protocol. We call this the pre-protocol, and these statements execute in such a way so that if one of the processes is in its critical section, it will delay the other process from getting into its critical section until the other one gets out of it. And then once a process gets out of a critical or as it exits a critical section, it executes a post protocol, and that post protocol makes it possible for the one that was waiting to get in. That's the general idea. Does everybody see how that works? And it turns out that it's kind of tricky, but it can actually be done in software. It's possible, there's several different solutions to it. It's actually possible to come up with some code for the pre-protocol and some code for the post-protocol that will solve the mutual exclusion problem, the critical section problem. And then last time we said that there were three, remember this? We said that there were three characteristics of a correct solution to the critical section problem. First, it must have mutual exclusion, which means what? Mutual exclusion means what?
Only one of them can be in critical section.
At the same time. Yeah, so, yes, that is correct. So only one can be in critical section at the same time. Freedom from deadlock means what? Just roughly speaking, not mathematically, but just roughly. Freedom from deadlock means what? That your program doesn't what? Freeze up. Yeah. Okay. So freeze up and not be. And then freedom from starvation means what? If one of them wants to do what? Wants to enter the critical section all the time, it will eventually do so. It won't be starved. Does everybody see? Does everybody remember that? And then we made that more mathematical. Here's the definition of mutual exclusion. Here's the definition of deadlock free, which is if some processes are trying to enter their critical sections, then one must eventually succeed. Because if some processors are trying to enter and none succeeds, then the system is frozen. Okay. On the other, and then that was existential. There exists a P range. P is trying to enter its critical section. Body P does enter its critical section. So there exists one that must succeed. But then starvation free is if any one process tries to enter its critical section, then that process must succeed. So that's a statement about every individual process. So that's a for all. So that's for all P, range P is trying to enter its critical section, P does. And then, which one was the safety and which one was the, safety and which ones were the liveness? Deadlock is safety and
Starvation is likeness.
and starvation and what was the third one? Wait, did you say, yeah, mutual exclusion is the safety property, deadlock free and starvation free are liveness properties. And then there's also this interesting relation between mutual exclusion, which is safety, and starvation free. Remember what that relationship was? One of them is stronger than the other. One of them implies the other. Which way is it? Yes, it was starvation implies. So which one is stronger? And starvation is stronger. Okay. If you say P implies Q, P is the strong one, Q is the weak one. Right. So here, starvation free is a stronger requirement than deadlock free because starvation free implies deadlock free, and we saw that that's relates back to what we learned in predicate calculus. This theorem 9.20.2. Now, okay, so now what we're going to do is we're going to spend a lot of time on the first attempt today. We might be able to get to the second attempt, we'll see. But we want to, but the tools that we use and the concepts that we run across in analyzing this first attempt are the tools and the analysis that we're going to use in general. So this will serve as an introduction to the general way to analyze a concurrent program. So now here are the general assumptions. Now actually here, let me write this. Remember what we have is, here's what we have. We have non-critical, actually I need a black pen for this, don't I? So remember there's 4 sections here. We have non-critical, we have, what was this one, the pre-protocol? Remember, the code, I'm talking about the code. Pre-protocol, and then this one was the critical section, right? And then we have the post-protocol. Is protocol C-A-L or C-O-L? O-L. No, okay. Okay. Now let's take a look at what our assumptions are. We have to have certain reasonable assumptions, right? So look, here's the first assumption. Once a process starts executing statements in its critical section, it must eventually terminate. Now, so here's the thing. If a process is right here, if a process is here, we have to assume that it's eventually going to complete. Because if you write an infinite loop in here and the process gets in here and he never completes, then I mean all bets are off, right? That's so bad. That's such a bad problem that we have to assume that it'll never occur. Why? Because if he does that, if one process gets hung up here, the other one will be what? Waiting to get in its critical section. Yeah, and no matter how good your algorithm is, you can't guard against that. You see what I mean? So I mean, it would be that's an impossible. If we don't make this assumption, the solution is impossible. You see what I mean? I mean, it's like how are you going to guard your program against an earthquake? Well, I mean, if an earthquake happens and your computer crashes, and the ceiling falls down on your computer, well, I mean, you can't you can't guard against that. You see what I'm saying? Not quite as extreme, but you see what I'm saying? Yeah.
I think the new iPhones have an app that makes it so when you drop them.
So the app when you drop it and then it knows that it's in free flight and then it does something to protect it when it turns. I think with hard drives, when they used to have hard drives in there, that was important for that. The head would retract or whatever. Yeah, anyway. So that's the first assumption. Now the next, but here's the thing. We don't make that assumption if the process is up here. See? If the process is up here, if one of the processes is up here and it gets hung up, that should not adversely affect the program. Is everybody with me on that? Okay? So the non-critical sections need not terminate. Furthermore, no variables in the protocols are outside the protocols and vice versa. So here's what's going to happen. This section, this section right here and this section right here, there's going to be some variables in there and they're going to be shared. But the only purpose for these variables is to control the access into the critical section. Those variables can't appear anywhere else in the program. In other words, it's not allowable for the program, for some other part of the program to muck them up, to like if one process says, oh, if I change this variable, I'll be able to get into my critical section before him, and so I'm just going to change the variable. You see what I'm saying? You can't. Are you with me on that? So no variables in one protocol outside. outside the protocols, and vice versa. And the operating system scheduler is weakly fair. Now, and you know that's a reasonable assumption. I mean, we have to assume that, you know, and that can be required, and that can be implemented by the operating system, by its scheduling policy. Because what the operating system does is it looks at all of these queues and each one of these suspended, you know, animation queues at these different, you know, in these different states, programs that are in these different states, and it can choose which one. And so the operating system's programmers can program that to choose one to say, you know, keep track of this one has always been wanting in, and, you know, we better let it in. You know, so the operating systems can schedule that. All right, now, so are you ready for our first big analysis, our first big attempt to solve the critical section problem? Here's our first attempt. This first attempt uses this single atomic await statement. Now, you have been introduced to this in a homework problem, right? Previous chapter, how the await statement works. All right? The post protocol is a single atomic assignment statement. And what it does, what this algorithm does, this solution to the critical section problem, is the processes take turns entering their critical sections. Okay? So here it is. Here's the code. Algorithm 3.2, first attempt. So what we have is, and then we're being very generic about, about our description, that we have the non-critical section is P1, and then what this, let's take a look here. This global variable turn, so they both have access to it. It's a shared variable, so, and that's how they communicate. And why do you suppose we call it turn? Because here turn gets 1, on line P4 turn gets 2, and on line Q4 turn gets 1. So why do you suppose we call it turn? The integer value of turn indicates what? Whose turn it is. You take turns, like you learned in kindergarten. Now children take turns, right? So that's what this does. This algorithm says now processes take turns, right? And the turn is the variable that enforces that. So what happens is we initialize turn to 1. Turn could just as easily have been initialized to 2. And what happens is no matter who starts first, you know, no matter which process the operating system picks to start first, what's going to happen? Suppose the operating system picks Q to start first, and Q goes through its non-critical section, and then he gets to Q2. But what happens when he gets to Q2? It says what? Await what? Turn equals 2. So he'll just sit in there, await. Eventually he'll time out, and the other one, and the other process will go through its non-critical section. But what does it say? Await what? Turn equals 1, and so, but turn is 1. So he will get into his critical section. He'll eventually get out of his critical section, and he'll set what? Turn to 2. So if he keeps going and he goes into his non-critical section, he gets to await turn equals 1, what happens?
Times out.
He times out because he's stuck there because turn is 2. And then and now the next time, eventually Q is going to get, if he's blocked at await turn 2, at Q2, eventually he'll get, eventually he'll be given cycles, he'll be scheduled, and turn equals 2 will be true. So he'll do his critical section and like that. Yeah.
One of the processes is waiting, and it won't do anything until it times out. Is the operating system, is that smart enough to just time out immediately?
That is a really, really good question. The question is, if one of the processes is at like Q2 and he's awaiting turn equals 2, the question is the operating system clever enough to actually see that he's doing that? The answer is no. And so what that means is that this is an inefficient algorithm. And what we're going to see is we're going to solve the critical section problem, but then we are going to see improvements to our solution later. And one of the features of the improvements of the critical section problem is to solve exactly that problem, the efficiency problem for why should it be spinning. So the answer in this particular, that was a really good question. So the answer here is no, it doesn't know. It just has to time out. Yeah, good thinking. Does everybody see what the deal is there? So yeah. So now here's what we're going to do. We're going to analyze now. You know, I just described this in English very simply, and you can kind of see what's going on. But we're going to analyze it in a lot of detail, and we're going to use some tools that we will rely on for analysis of other concurrent programs later on. So first of all, let's make sure. Remember one of those requirements. Turn is a variable that turns in the pre-protocol and the post-protocol. So P2 is the pre-protocol, and P4 is the post-protocol. And same with Q2 and Q4, right? So notice that turn, first of all, variable turn cannot appear in the critical section or the non-critical section. So we assume that that's the case, right? Now, and here's another question. Another question is, how do you actually do the await statement? Because there is no await statement in Java, and there's no await statement in, there's not even an await statement in C++. So here is the way it's done. Here's the way you do it. And you can also do this at the assembly language level. So this is, and the construction is called a Spinlock. Now, why do you suppose, well, actually, what is a Spinlock? A Spinlock is a technique for implementing the await statement with a loop. So look, when in the program, here, in this solution here, when it says await turn equals 1, the way you do that in the program itself is you say while turn is not equal to 1, and then you have an empty C++ statement. Are you with me? Now, why do you think it's called a Spinlock? Because what's it doing? Testing, 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 and pretty soon, and eventually, not necessarily pretty soon, but eventually testing, eventually what? Time out. Right? It'll just keep, if it has control of the CPU, it's testing, testing, testing. Eventually what? Time out. Well, hopefully what happens is, after timeout, some other program will do what? Change the value of what? Turn, and then when it gets the CPU testing, whoop, I can go. Now, does everybody understand the, you know, what's going on there and how it depends on the timeout? Okay? So now, here's the thing. This timeout is a while statement, right? Here's the question. How many critical references are in the Spinlock? You remember the definition of a critical reference? What's the shared? It is 1. What is the critical reference? Turn. Yes. It's this turn. It's this turn not equal to 1. So this is a conditional statement that's either true or false, right? So it's in an expression. This is in an expression, but it's done what? It's assigned in the other one. So there's 1. Good. What does that mean? Well, it's not a close. It's actually not atomic, but what does it mean? It does satisfy limited critical reference, and so therefore, even though it's not atomic, what do we know? We can analyze the algorithm as if it were atomic with no problem, with no fear. Right? Does everybody see? So as long as the other statements in our solutions have at most 1 critical reference, the problem satisfies LCR, we can analyze it as if the statements are atomic. So you see when we come back here and we look and we see await turn equals 1, and that's one statement, and we consider that to be atomic, even when we implement it, we know that we can do it as an atomic statement. All right? Now, you guys, we're going to do a class exercise. So is everybody ready? I need a darker pen. So focus on the board here, because what we're going to do is we're going to look here, and we're going to do some stuff here. Now here's what we're going to do. We're going to analyze this by doing a state transition diagram. And in each state transition diagram, in each state, what we're going to write down is the statement in process P that's going to execute, that's able to execute next, the statement in Q that's able to execute next, and the value of turn. So what we're going to do is we're going to start here, and we're going to do P1, Q1, 1. All right, is everybody with me? Does everybody see what we're talking about here? What the state, so here's the code's on the slide, and here's the state transition diagram. Are you with me? So now here's my question. If P1 executes, what happens? If P1 executes, what is the next state? So I'm going to put P1 here. I wish our author would put which one executes on the thing. It would make it easier. But anyway, so what will this look like? P1, Q1, 1. If P1 executes, then what is it executing? It's non-critical section. So now the next state would look like what? It would be P2, Q1, and what would the value of turn be? It would still be 1, right? Now, on the other hand, if we're in state P2, Q1, 1, and, oh, wait, I should not have put P1 here. I'm going to say P executes. Say P. Now, if P executes again from this state, where will that put us? Well, but what will the state, then which statement would be executed, would be possible to execute next? P3, right? Is everybody with me on this? P3. Q1 is still here. But now what happened to the value of turn? Oh, did it stay the same? Oh, you're right. It did stay the same. Okay, so this is what happens with P. All right. And now, what about, oh, you know, I think my geometry is not very good here. And now what would happen if P, what would happen if we do P again? If P executes again, that would be what? P4, Q what? Q1 and? P4 hasn't executed yet, so what? 1. And then again? P1, Q1, but this time what? 2. Okay, so these are all P's. Now, what about a Q going from here? What would this be? P1, Q2, 1. And then what? If we do Q again, what? Ah! Now, how are we going to indicate that? Because if Q2 executes, where does it go? Which state does it go to if Q2 executes? Back to itself. So does everybody see that that's going to be this? Are you with me? Okay. And now let me see. Can we do another one? Another interesting one here. If this is, well, yeah. Let me see. How about it? Can we do a Q from here? And then, so what would that take us to? So here we did a P and a Q from here. Here, actually, here this is a Q. This is a Q. This is a Q. No, sorry. We did a P and a Q from here. We did a Q from here. Can we do a P from here? And where would that take us? P2, Q2, 1. In fact, that's the only way we can get out of this. That's if P executes. Okay. Now let me see. What other interesting, can we do another interesting one with a transition? What can happen here? Can P happen here? Okay, well let's go on down and see. And then what happens here? P2, Q1, 1, 2. Can P happen again? Ah, so if P happens here, what happens? Now that's a loop. So there's a, yeah, that's another end. Now, do any of these things close in on each other? I mean, how many possible states are there? Are there a finite number of states in this algorithm? Do you see what they are? There's all the combinations of P's and Q's and values of turn. Okay, so let's see. Oh yeah, here is the start of the analysis. And now, how can we get these? Did we do our loops right? We went down instead. Yeah, our geometry was a little mixed up. But how did we get to P2Q21? P2Q. Here's P2Q21. What's another way to get to P2Q2? It looks like he. Oh yeah, we can go from here. Oh right, if Q executes from here, then that's P2Q21. Yeah. Right. The geometry is just rearranged a little bit. So everybody, but anyways, everybody see how to do a state transition diagram? Now, so that's the start of it. Here's the whole shebang. So remember, I said how many states are there? Well, you can count them up. How many are there actually? 1, 2, 3, 4, 5, 6, 7, 8. Looks like 16. There are 16 states. You can arrange them like this. And did we do it right? And see, it'd be better if you put this transition is on a P and this transition is on a Q. Are you with me? Does everybody see how that works? So now, what you could do, one way to analyze this is to do a complete state transition diagram of your algorithm. And there's actually software that helps you do this. And I actually have I have an article or two on the web page that shows you know, it'll automate. It can go through and analyze your program and automate and do all the state transition, do the whole state thing for you. But now, supposing then that you either were very diligent and you constructed this yourself, or you had the computer analyze your algorithm and did this. How can you use this state transition diagram to answer those, to see if those 3 properties that we want actually hold? See? So how can we analyze mutual exclusion? Well, let's go back. What does mutual exclusion mean? Mutual exclusion would mean what? Let's go back to this code here in algorithm 3.2. Yeah, they're not both. Yeah, yeah, P3. Right, but then what would the state be? What would the values of the 3 things in the state be if they were both in their critical section? It would be what? It would be P4, Q4. Are you with me? Because P4 would be wanting to execute next, and Q4 would be wanting to execute next at the same time. Is everybody with me on that? The state. So you would look for P4, Q4, and any value of turn. So let's go. Let's look for that. Whoops. Is there a P4, Q4? And so there it is. This is kind of like brute force.
P3, Q11, can we do Q2 twice?
Well, I know that it doesn't say, I know that that we have mutual exclusion in this algorithm. So that's not the question. The question is whether we indicate that by P3, Q3 or P4, Q4.
Yeah, with this algorithm you couldn't get Q4.
And that's why we look. That's by inspection. By inspection, if we look at this, there is no P4, Q4.
But you also can't put all 3 either. There's no P3.
But there's also no P3, Q3. But what I'm saying is P3, Q3 means P3 is about to have. Let's go back to the code.
So are these definitely not showing the ones that are currently that?
This shows all. This analyzes the transitions and shows every possible state.
Right. But maybe rather than showing the ones that can execute
No, no. No. Look here. The start state is P1, Q1, 1. That means P1 is going to execute next, and Q1 is going to execute next, and the value of turn is 1, and whichever one executes, that takes you to the next step. These are the ones that are going to execute next. It turns out that P3, Q3 is also impossible to appear. Because what would happen is this would have executed, and this would have executed, and this would have executed. So they are related. In fact, it's even answering the same question. So, oh yeah, I see why I put P3Q, because it's actually answering the same question. It's one step ahead. Yeah. Is everybody good? Man, we really analyzed that one to death. Okay, so there's mutual exclusion. That doesn't appear. Conclusion, we have mutual exclusion. Now here's the problem. Now watch this, you guys. We just had this big discussion. Watch this. That is a whole lot of states, right? 16 states. Well, look. Do you see? So here's the next concept in our analysis tools. There's too many states to examine. But look at this. Why don't we just omit P1 and P3? Because what is P1? That's just a what? Non-critical section. What happens there is irrelevant. You see what I mean? And furthermore, what about P3? That's just the critical section. What happens there is irrelevant. Right? Because it's not controlling anything. So look, we can actually do, this is an abbreviated analysis. It's just await turn equals 1 and turn gets 2. Await turn equals 2, turn gets 1. And it's going to tell us the same information. Now, how many states for this one? Okay, let's do this one. Now it's P1, Q1, 1. That's our start. And now what happens if we do P? It's going to go to what? Oh, P. Can we do P? Yes, we can do P. So what will it go to? P2, Q1, 1 still, right? But what happens if we try to do Q here? It will loop. So here is Q. I mean, it will await, and so it will go back to the same state. And what happens if we do Q here? Oh, no. Oh, sorry, that is what we just did. Sorry. Okay, and now what happens if we do, oh, you're right, that is what we just did. And now what happens if we do, can we do P here? And what happens if we do P here? Q1, 2. And what happens if we do Q here? Q loops here. And what happens if we do, can we do P here? Well, if we do P1, what happens? It loops. And if we do Q from here, what happens? P1, Q2. And then and the value of turn? 2. I'm running out of ink here. And then what? So here's the P, we have a P and a Q from here, we have a P and a Q from here, P and a Q from here. And now what about this? What about if we do P loops on this one, and then what does Q do? Goes back up to here. Is that, are you with me? There it is. Yeah, I think it's better. This time I think our geometry is better than that one, right? You see what I'm saying? I mean, but it's the same thing, right? It's the same connection. It's the same connection, but yeah. But anyway, it's the same thing. Are you with me? And he's got more detail here. Oh wait, he actually writes out the statement, you know. Okay. But look, it's the same kind of thing. Because now let's ask the question about mutual exclusion. See, in this one, now what state do we look for? if they were both in their critical section, now it's unambiguous, right? Last time we said, oh, it could be, we could be looking for P3, Q3 or P4, Q4. But now, what do we look for mutual exclusion? We're looking for P2, Q2? Yes, because if P2 is going to execute next in P and Q2 is going to be executing next in Q, they would both be in their critical section. So we look for the absence of P2, Q2. Well, what about P? Do we have a P2, Q2 here? No. Therefore, we're good. Analysis of mutual exclusion, P2, Q2, 1, or P2, Q2, 2. And the answer is no. So conclusion, we have mutual exclusion. Now, do you see how that works? I mean, how that works? Now, how about deadlock free? Deadlock free. Yeah, now that we've done the abbreviated one, let's do the, let's.
What about, shouldn't we do starvation first? So that we don't have to do this one?
Well, let's do this one, and then yeah, you want to, I could count on, yeah, do as little work as possible. Write down as few, I know you. It's always asking me, well, can I just write down this instead of putting this into proof? Yeah. That's pretty funny. Okay, so no, let's, for it to be deadlock free, how do we check the state transition diagram for deadlock free? Well, what about P1, Q1? I mean, here's P1, Q1.
Yeah. They're both trying to enter their critical section.
Well, I mean, the fact that you're in P1, Q1, the fact that if you're in P1, Q1, what's going to happen? You have a what? You have a way out. In other words, you don't have going into one state and no way to, and looping to itself. Is everybody with me on that? So you see, so in what state are they both trying to enter? In states P1, Q1, and P1, Q2, 2. But we deduce what must happen from one of these states. You see? So here's actually, if you want to do it in infinite detail here, I used his figure here, and I kind of shaded in this, the start state here. So if we're in state P1, Q1, 2, which is this one, so they're both trying to enter, and this implies, now what are the transitions here? Q selected, this implies by virtue of the fact that Q is selected by weak fairness, okay, so because Q1 is awaiting. So if Q1 is selected by weak fairness, that gets us to P1, Q2, 2 to this one, right? And then, but now, what did we say? When Q1 was in its critical section, what was one of the assumptions? That once it's in its critical sections, it must complete, right? So once it completes, it will be selected by weak fairness, all right? And we'll get back to P1, Q1, 1, okay? And so, and the analysis starting with state P1, Q1, 1 is similar. So if some try to enter, one must succeed. So therefore, the conclusion is that it's deadlock free. It's kind of like looking at this and saying, you know, oh, well, by weak fairness, this one will eventually get picked, and so it will go to here, and if it's in its critical section, we assume it will finish its critical section, and therefore, by weak fairness, it will be completed, and boom, it can go to there. Okay? So it is deadlock free, so that's good, but what's the problem? If any tries to enter it, it must succeed.
Is weak fairness guaranteed by the operating system?
It is guaranteed by the operating system. That's how we have to assume that the operating system can schedule with fairness, with weak fairness. Okay? So now, let's take a look and see if it's starvation free. Now here's the problem. Now check this out. I have annotated his diagram here. Let's suppose that, and these red arrows mean that we're in the state. Where is this state on the figure? My shading didn't show up. Can you tell that's a little darker? On there, it's good. So do you see it's P2, Q1, here, it's P2, Q1, 2. It's like right here, right? Now, if we are in this state right here, and now where is this? So Q is, where is Q? Q is in its what? Non-critical section. Now, what did we say about the non-critical section? Could happen. It doesn't have to terminate. So P is trying to enter its critical section. Q is in its non-critical section up here. Q need not make progress, so this Q need not make progress. But if that Q doesn't make progress, what will happen? Because what is that transition there? Whose transition is that? Yeah, so P is starved. Wait, is that right?
No, that's
Yeah.
because P2.
Q need not make progress, so P is starved, right? Is that right?
Because whenever P is
So, like, if-
checked, it just moves to the.
Yes. Yes.
Non-critical section is like 1,000 lines long. The Q would just be in there for a long time.
Yeah, for a long time, but even if it hangs, our assumption is that it's possible for it to hang in its non-critical section, and the algorithm still has to work. It still has to be starvation free. Okay? So our analysis is the first attempt is not starvation free. Now what I want to do is we're going to finish by doing some demos. Now watch this, you guys. We're going to do spin loops, spin locks now to do it. So check this out. Okay, so here's our demo. Notice here we have our global variable n initialized to 0, and here is our global variable int turn initialized to 1. And here's the code for the process P. And so what we have here is, here's our local variable integer temp, and for int I gets 1, I less than 10, I plus plus, and here we have a little cout statement to trace the value of I, and here's our random delay. And now check this out, here's the spin lock. It's while turn is not equal to 1, do nothing. And so this awaits. This is await turn equals 1, and we do that with this spin lock. So here's our critical section. Temp gets n gets temp plus 1, with a random delay here to make sure that we can get some interleaving. And then the post protocol is turn gets 2. And now here is the same code for Q run, for process Q. Same loop, same cout, random delay of between 1 and 10 milliseconds, 0 and 10 milliseconds. And here's the spin lock for Q. It's while turn is not equal to do nothing. So this is like await turn equals 2. Here's our critical section as before. And then here's we start P with P run, we start Q with Q run, then we join them, and then we output the value of n as whatever it's supposed to be. Okay, so now what do you suppose the output's going to be when we run this? Will it be correct? Yes or no? Well, check it out. Here comes our first run. Boom. So what happened here? Oh, look, we had some interleaving. We have I equals and then I equals. So we had some interleaving there. So anyway, they start off to be 0, 1, 1, 2, 2, 3, 3. The value of n is 20. Seems to work correctly. Let's try it again. What do you suppose? Oops, here we go. Oh, it's still 20. That's interesting. Oh, here, look, we had some interleaving at a different location here, at this spot right here. That's because these output statements are not inside the critical section. You see, they are outside the critical section, so interleaving can happen outside the critical section. But it apparently did not, but the interleaving did not happen inside the critical section, right? Because we got 20. Let's try it a couple more times. Still 20. One more time. Still 20. It seems to be working correctly, would you say? But there is a problem, because what if we go up here to P, and instead of having it execute 10 times, suppose we have it just execute like 8 times. Now what's going to happen? Can you predict? Let's clear it this time and start over fresh on our display. And here we go, run, and
Oop. What's happening? We didn't get to the end. Wait. We are stuck here at 8. What's going on? Ah, you see? We had some interleaving here at the beginning. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8. But now we are starved, right? It looks like that Q is being starved because P quit. See, you see what happened is P quit and Q is waiting for its turn. But because P quit, Q is waiting for an event that will never occur. So that's a deadlock. Well, it's kind of debatable whether you'd call this a deadlock or starvation because Q is being starved. At any rate, the only way that we can proceed, you see this process is still running. You see, it's still looping and spinning. And so, in fact, if we go to the activity monitor, look, here, let's do that. Let's go to the activity monitor. So we'll, and look, here's our activity monitor. And look at algorithm 3.2. It's taking 99.8% of the CPU time. It's spinning. That Spinlock is just spinning and is chewing up those resources. Look how hot that is. Man, isn't that a demo? So there's the activity monitor that shows you how the fact that lock is still spinning, and the only way that we can stop this thing is to externally interrupt it. So we'll click this and boom. And now if we go back to our activity monitor, you'll see, well, it's no longer running. The process died. All right, so that's our demo of C++.
And so we'll take a look at the Java code and then continue with our attempts next time. But I thought that was a pretty slick, pretty interesting demo, and we have some analysis tools now to help us. All right, good deal. See you next time.